The idea that there are different sizes of infinities comes from German mathematician Georg Cantor, who lived from 1845 until 1918. Cantor studied set theory and identified two types of infinities, countable and uncountable. The difference is this: members of a countable infinity set can be listed out, while those in an uncountable set cannot be listed out. Natural numbers are countable, because even though in reality a person could never write down all of them, there is a clear method to do so. In order to understand these two types, we're going to look at an example involving rational numbers and real numbers. The set of rational numbers, represented by the stylized q, contains all numbers that can be expressed as a fraction. Real numbers are represented with an r, and they include all numbers on the number line. Rational numbers are real numbers, but so are irrational numbers, values such as pi that can only be expressed in decimal form and continue on with no pattern. Both rational numbers and real numbers are infinite, but is one of them bigger than the other? To answer this, let's look at their types. Rational numbers are countable, while real numbers are uncountable. Cantor's diagonal argument proves this categorization. Let's start with rational numbers. Is there a way to list all of the fractions out in a regular pattern? A number line won't work because there are infinitely many fractions between each pair of whole numbers. So instead, Cantor set up a grid. The numbers along the top are the numerators, while the ones along the left are denominators. In order to list every fraction, Cantor went through them in a specific path. You can see that the curve provides us with an organized method to hit every rational number. This proves that the set of rational numbers is countable. Now it's time to show that real numbers are uncountable. But if rational numbers are part of real numbers, how can they be different types of infinity? The reason is because the non-rational real numbers, irrational numbers, are uncountable. Cantor proved that in this way. Suppose you have a list of irrational numbers. Then say you decide to make a new one by taking the first digit from the first number, the second from the second, and so on. Next, we take this number and make another number by changing each digit to be the next numerical one. This new number would be completely different than any other on the list because it has a different first digit than the first, a different second digit from the second, and so on. No matter how many numbers are added, this process can always be repeated to make a new number, and thus irrational numbers are uncountable. Cantor realized that uncountable infinities are larger than countable infinities. This is essentially because, well, uncountable infinities have too many members to count. While in countable infinities every member is theoretically known, there is no possible way to ever know the numbers in an uncountable set. Thus, the set of real numbers is larger than the set of rational numbers.